Hi, and welcome to practice problem 2 of circuits analysis. And in this problem, we're going to be finding the per unit impedances of a somewhat complicated one-line diagram. So the question asks, what is the per unit impedances of all components? And we're assuming the generator as the base. So I like to write the bases in each zone. And remember, a base consists of a apparent power value and also a voltage value. So in our first voltage zone, S base is equal to 1500 kVA, which is our generator, and then V base is equal to 480 volts. And I'm going to, since it's on the primary side of this transformer, that's going to give us the base for this first zone. And then I'm going to go to the secondary side of that transformer, which is also the primary of the secondary of the primary of the second transformer. So power bases are going to be the same in each voltage zone. So S base is equal to 1500 kVA, and then V base, we have to transform it over. Since we're starting on the primary side, we start there and then we transform over given whatever transformers we see. So we're given a 650 to 1000 volt transformer, so we're going to transform it over to the secondary. So 480 times 1000 over 650. Put that into my calculator, and you will get 738.5 volts. So the new voltage base on this side is equal to 738.5 volts. And then we're going to have one more zone because we're hitting another transformer. The power base is going to be the same. S base is equal to 1500 kVA, and then V base is equal to, we're going to transform this 738.5 over. So this transformer has 1000 to 600 volt. So just slightly different. Put that into my calculator. I'm going to get 443.1 volts. So the voltage base for these motors over here are going to be 443.1 volts. Now I'm going to convert all of our per unit impedances for each individual component. Okay. So we weren't given one for these transformers just to make it a little bit easier. And so we're only going to be given the per unit impedance here for these motors. So it's 7%. So I want to convert that 0.07 times S new base over S old, and then V old over V new squared. So this 0.07, its old base or whatever it was based upon, is the rated components, the rated values of the motor. So 0.07 times the old power, which is 150 kVA. The new power is going to be 1500 kVA. The old voltage is 480. The new voltage is going to be for this zone 443.1. So I'm going to put that into my calculator. 0.07 times 1500 divided by 150 times 480 divided by 443.1 quantity squared. I'm going to get a new impedance 0.82 per unit. Okay, so I've just converted this per unit impedance to this new base, which is based on the generator. And I can do the same thing for the motor. So I'm not going to start with the original equation again. I'm just going to take these values, 0.05 times the new value, which is 1500, the old value, which is the rated of the motor, which is 100. Then our voltage is still 480 old, so that's on the top. And then the new was 443.1. And we're going to get 0.05 times 1500 divided by 100 times 480 divided by 443.1 quantity squared. And I'm going to get 0.88. So 0.82 per unit. All right, let's just assign some values, just for practice for our transformer here. Switch to a different color for this transformer. Let's just assign Z is equal to 5%. For this one, Z is equal to 5% here. And I just wanted to clarify because sometimes people get confused, like which voltage base am I supposed to use? And the answer is that you just have to be consistent. So if I'm using this voltage base 480, the new one, then I have to use my 650 here. And if I'm using 738 for this transformer, then I have to use 1000. So I'm going to stick with the 480, and I'm going to convert this 1000 kVA transformer with Z is equal to 5%. So we're going to go 0.05 times my new power value, which is 1500, my old power value, which is 1000, and then I'm going to use the primary side as my old voltage, which should be on the top, so 650, and then my old voltage, my new base voltage here is 480, and that's going to be quantity squared. So 0.05 times 1500 divided by 1000 times 650 divided by 480 quantity squared. And this Z is equal to 5% is going to be converted to 0.14 per unit. And we can do the same thing for this Z is equal to 5% for this transformer as well. And I will do the same concept, 0.05 times 1500 over 1000. So new power over old power. We have 1000 volts old, so 1000 on the top. And then for this primary side of this transformer here, we want 738.5 as the new voltage. Let's plug all our values in. And you will get Z is equal to 0.14 per unit. Okay, and you can see that we get the same conversions here. Well, pretty similar. They're slightly different because of that these voltages here are a little different here, so they're going to be slightly different. But if you were to use the same transformer and then use the voltages on the secondary side for this case, you should get exactly the same answer. And the reason why is that these ratios of voltages are going to be the same regardless if you're looking at the primary side or the secondary side. So on the secondary side, I'm at 443.1. Compared to not 1,000 but a 600 as the old base. And you should get Z is equal to 0.14 per unit. And just to further hammer that in, let's look at those specific voltage ratios. So our old over the new on the primary side, and then on the secondary side. So for this transformer, the old is 1,000. The new on the primary side is 738.5. And that ratio is going to be 1.354. And on the secondary side, the old is going to be 600 volts. The new is going to be 443.1. And we should get the same exact answer, besides some rounding that I did. So 1.354,096,096. So you can see that regardless of whether or not you're comparing the primary side or the secondary side between your old base and your new base, the resulting per unit values are going to be the same. And that's actually one of the main reasons of using the per unit analysis.